Swayam Prabha. Digital India. Educated India.
Okay, so yesterday I did something about this developments in Indian mathematics in arithmetic, basically decimal place value system, then some amount of algebra, geometry and combinatorics, and I had started in trigonometry. So I will continue with trigonometry, development of trigonometry in India. So I talked about how it is defined, jya, okay, or jiva, which is essentially the, if you have a circle of radius r, so if this is the angle, so then this is radius, and r sin theta is this, suppose this angle is theta, so this r sin theta is this, that is the jya, okay. But they don't ever talk of angle, they always talk about arcs and distances, okay. That is how it is done in India, but it is essentially the same thing except for a factor. Normally it is taken to be the circle of radius 21,600 minutes. 21,600 is 360 into 60. So that is each minute of angle corresponds to unit distance in the circumference. So that is how it is, 21. So the radius will be 21,000 by 6,000 by 2 pi, which is nearly 3438. Okay, but not always so, because I don't have time to go through all this, because Indians are always, very keen to simplify things, so that it can be not only for scholarly people, for other people also, it is easy for computation. So many times they will go for lagujya, small r signs, especially Bhaskara and all that, they did it, for r is equal to 120 they took, and things like that. Anyway, so now I didn't tell you how to find it, okay. So it was defined, but did they find the values? Yes, they had a way of finding the values. So that is what I will this thing. So normally a quadrant is, you remember, is a 1/4 of a circle, right? It is divided into 24 equal parts, so that each arc bit, okay, so that is equal to 90 by 24. So that is 3 degree 45 minutes or 225 minutes. So then the procedure for finding r sin I alpha, I is equal to 1 to 24, is explicitly given. As I told you, r is normally taken to be 3438. Okay. So that is, see, suppose this is P3, right? This point on the arc. So this corresponds to 3 degree 45 minutes into 3. Okay, that is the angle. So, but they always talk about the arc. So this will correspond to 225 into 3, 775 minutes. And this is P3, you drop a perpendicular to this. So this is this r sin 3 alpha, alpha is this. Okay. So similarly for other things, okay. And r sines is the intermediate angle. So you will get only sine of 3 degree 45, I mean 3.75, 7.5, like that. Okay. How about intermediate angles? It is done by interpolation. Okay. I will come to that. So now this finding the values for these 24 r sines, jars, So interestingly, Aryabhatiya, he gives this thing, a difference equation for this, So he says r sin I plus 1 alpha minus r sin I alpha is very close to r sin I alpha minus this minus this, okay. So this is the formula he gives. So tables of sines are generated from this. With r sin alpha is r alpha, because for extremely small arcs, small angles, the arc and the distance, that perpendicular, will be essentially equal. So that's 225 minutes. So that is the only input. So then you can get all these things. So now I have to remark about this, what exactly is mean and what is its significance, okay. See, now you see, this one is called a sign difference. It is difference between the successive sign, okay, for I plus 1 alpha and I alpha, you see. So it is a difference. It is sometimes called first order difference here, okay. So now this is also a difference, but the previous set. here I plus 1 and I are there, here I and I minus 1 is there. Okay. So now this minus this is equal to this, if you take it to the left hand side. So this is called a second order difference. Sin I plus 1 alpha minus or sin I alpha minus of this sin I alpha minus sin I this. So that is equal to this. So it is absolutely amazing that Aryabhata realized this, because this second order difference is proportional to R sin itself. This is essentially equivalent of this d squared sin x by dx squared is equal to minus sin x. I don't know whether you people know this. Okay. So this is a sin x differentiation. So this is, of course, I am not saying that Aryabhata knew derivatives or he knew differential equation, but it is equivalent to that, and it is the what can be called a discrete version of the this differential equation. Okay. So a lot of people have wondered about important mathematicians, like Mumford had come, we had a series of lectures about 15 years, but he was also a field medalist, important, most prestigious prize in mathematics. So he was, there was a series of seminars on, development of calculus in Europe and India. So then he was mentioning that, how it is a very amazing thing for that time. Yeah, of course, yes. Alpha has to be sufficiently small, and 225 is somewhat good enough. Yeah, it is good one. So that's the thing. Yeah. And also, this is one way of, so then he will give a table based on this. So only input is this, the first sign, and then you can get all the things. Okay, and this, he writes it as a table. Okay, these differences, the sign differences, he gives it as a table. Okay, so everything is, because everything is very brief, is, it should be, you'll be able to remember that. And he had his own notation, this thing, convention for numbers. So in his convention, of course, if you want to understand, then you will be able to remember and will, So the whole sign table is given in a verse, which says Makhi, Khaki, Bhaki, Fakhi, and all the Nyaki, all things like that. You see, the 24 R signs are given in that. So this is very amazing. So from that one can construct the sign table. Yeah, this is the, this is, see, sin I plus 1. Yeah, you see, suppose you take this one, you see, this is P23 and 23. So that is R sin of 23 alpha, and this is R sin of 22 alpha. Okay. So now this minus this, so that is the difference, First, this first order. Now suppose you take 22 or 21 also, you see, I have not written it. So that is R sin of 21 alpha. So now the first order difference is, 22, 23 minus 22, and the other is 22 minus 21. And the difference of these, so that is the second order difference. And so it will keep on decreasing. These differences will keep on decreasing. One can see that, that is the, yeah.
Sir,
okay.
Could you repeat the verse you said in Sanskrit and what it means?
Which one?
For the sign table.
Yeah.
What was the verse? And what does it mean?
Sorry, I didn't get that thing, Yeah. So there is this thing, verse. I have forgotten the whole verse because I have forgotten the Aryabhata convention. It is slightly unusual. I will tell you sometime, Yeah. Yes, tell me. Yeah.
So, what were the words?
Which one?
For sign? What were the words you said?
So, sign, the word is ja.
Ja.
Yeah. Ardhaja, and then it became ja. Yeah. Or jiva. Yeah.
Sir, Aryabhata created this convention to represent the signs of these particular angles in the form of a verse.
Yeah.
So, if he were to teach this to someone else, how will that other person know what the convention is using if he is not teaching?
That is, he didn't give it. We don't know how he did it because he has given just Aryabhata is known. But there is his commentator, Bhaskara one, as I told you, he gives all the details. He gives the details in his commentary called Aryabhatiya Bhashya.
So Bhaskara is the one who told us that this means this angle, this means that angle, that means that.
No, it would have been known at that time. See, like teachers would have told people, students, so they would have told verbally, but written down version, which is available to us, that is by Bhaskara. Yes.
Sir, and this is all 24 values.
Which is 24 values. Yes. Yes. So he gives, and he gives another method also, because you see sine of 45, of course you have to multiply by this thing. Sine of 45 is, what is sine of 45? 1 by root 2, you know that. And sine of 30, 1 by half, okay. And sine of 60, yeah, okay. So then this is there. And then they also knew, that what is sine of r theta 1 minus theta 2. And they also knew what is sine 2 theta, the formula for those things, And also, of course, knew that cos is square root of 1 minus sine square. Using all these things also, and using sine 30 is equal to half and sine 45 is equal to 1 by root 2, it will be generated. The whole sine table can be generated geometrically. But it will have a lot of roots and all that and highly cumbersome. And so this is the table which he gives without using this geometrical construction. So geometrical you can get exact formula. Okay. And whereas these things, as you see, is somewhat slightly approximate. Now, how about, so this is the sine table according to, this is Aryabhatiya, and also the great Bhaskara, 12th century, he also gives the same thing, okay. This is sine, sine values itself, and then there is one astronomer and mathematician called Govindaswamy, about around 8th or 9th century, so he gives these values, and Madhava series if you take, okay, then these are the values. Now I should explain what it means. Here theta is in minutes, okay, so 225 minutes, so this is 3 degree 45 or 3.75 degrees, this is 450 minutes, so it is 7.5 like that, etc. Okay, and it's like 1125, that is 1125 by 60, 18.75 degrees. And what does this mean? For instance, you are getting 3 numbers are there, right, separated by this thing. So this means these in sexagesimal units. So 1105 plus 1, that is must be divided by 60, and then this must be divided by 3600. So this is what it is, And as you know, r sin theta is 3438 into sin theta. This slightly approximate, but far more r value, very accurate value of r also is given, you see, later the very accurate value of r, it is not, it is 3437.74 something and all that, so that is also given, the accurate value of r. But because it is astronomical, yeah, I will come into that straight away, yeah, astronomical, yeah. And that is in the context of astronomy that this comes. Yeah. And for intermediate angles, there are many texts. Even Bhaskara one also says. So they say this is the formula. This is how you have to do. So sin theta is there. So which is between theta I and theta I plus 1. Okay, theta I is I into alpha. Theta I plus 1 is I plus 1 into alpha. Suppose theta lies in between. So then this value. Sine for this angle and sine for this angle, okay. So take this. So then the sin theta is r sin theta plus r theta minus theta I into this by this. So this is the interpolation formula. Why is that? It is easy to understand, because the thing is, you see, this is the difference. See, between theta I plus 1 and theta I, this is the difference, right, for this arc difference. So what is the difference for this arc difference, theta minus theta I, r into theta minus theta I? So that is this. So just straight away proportionality principle. Then you have to add the value for this. So this is the proportionality principle, which is used everywhere, in Indian astronomy and mathematics. And this is there in Ptolemy also, this kind of proportionality principle. But what is amazing is in Khandakadyaka, Brahmagupta, that is in 7th century, he gives a second order interpolation formula. So this is only correct to order, first order you say. I don't know whether you heard of Taylor series. Yeah, this is first order Taylor series basically, if you consider this as some derivative. So this is the second order thing he gives. Yeah. So many ways. I'm coming to that now. Where exactly they started this calculus business. I'm coming to that. Now, in his Bhaskara 1 also gives a formula for this. R sin theta just as a ratio of these two things. Quadratics in theta. This is the theta is in degrees and theta is in radians. You can convert it into this. So this just they give the formula. Of course, they have not explained it. Bhaskara 1 also has not explained it clearly. But later people they can if you take it as some ratio of two polynomial these things quadratics and then make it optimal, then this is what you will get. Okay. So this and it is amazingly accurate. This is the the percentage error is so small. See, for most of the range you can say it is 0.1%. What the formula gives. I mean, just give the formula for the sin theta. You see, you don't have formula for that, right? Which you can immediately use. Of course, nowadays you use calculator. But suppose you didn't have a calculator, how do you get for an arbitrary value? For arbitrary value between 0 and 90, you can use this. No, Bhaskara doesn't seem. Not Bhaskara 1. No, he didn't seem to be this thing. There is no evidence. Only infinite series starts with Madhava and co only. And the comparison between this, in fact, I drew this thing. You can't see the difference between the actual sin theta using a calculator and Bhaskara 1's formula. Of course, if you make it very this thing accurate, expand it, maybe you will this thing, but it's very little. That's the thing, amazing. Yeah. Binomial theorem, maybe they had some vague idea, but it will come later. But he thought of this, that is very interesting. Yeah. And he says is due to Aryabhatiya has thought about it like that in his commentary, he says. So, to conclude about trigonometry, the modern form of trigonometry is close to the Indian formulation of it. And beginning with Aryabhata, many contributed significantly. Varahamihira himself, these things, he has in this work called Panchasiddhantika, this thing, and Bhaskara 1, Brahmagupta gives. In fact, Brahmagupta, he very clearly says, that this in a triangle, you know the relation between sides and angles, right? Sin A by A is equal to sin B by B is equal to sin C by C. Are you aware of that? Yeah, that is there in Brahmagupta's Brahmaspata Siddhanta. And Bhaskara 2 takes it significantly forward in Jyotpatti and other parts of Siddhanta Shiromani. And see, the word also is interesting, how they viewed these things, because they wanted to calculate things, So, Ja is sign and Utpatti means generation in Sanskrit, okay? So, they are generating signs. And not that, these theorems about Ja and all that comes in Jyotpatti, some theorems come. But the main thing is to generate signs. So, like in Panini, the main thing is to generate all valid words, kind of thing, yeah. And he also gives this composition law. It's called Jive Paraspara Nyaya. Nyaya is rule. Jiva is sign. Paraspara is mutual. Paraspara is mutual. You see, because you sin theta, then cos phi, and cos theta and sin phi. So this is. So now we'll move on to this calculus ideas.
Why didn't they think of cancelling out the r's? Do we know any reason?
They didn't take cancel out r. They didn't say that because they were calculating r sin theta. Yeah, so they so r sin theta, r cos phi you take and add and this thing subtract, then divide by Trijya they say. So that will give the Jya of the arcs corresponding to theta plus minus phi. That is how they did it. Yeah. So now the derivative of sine in comes So this is a little technical because people are not very much used to astronomy. I see that, because normally nowadays when you say astronomy, normally you mean astrophysics, right? Astrophysics, then immediately you go to black holes and dark matter and all that. No. The astronomy, old astronomy, you see old astronomy everywhere in all countries, all civilizations before, let us say, 16th century, okay? 17th century, say 7th century beginning, the things changed because of the telescope, okay? So, before that, you can say the old astronomy, So, in that, you see, the main thing was to find out the positions of the planets, okay? And my positions of the planet, what we mean is, of course, daily we see that sun or moon rises in the eastern part of the sky and goes up and then comes down and sets in the western portion, okay? So, that is called the diurnal part, but I am not talking about that. I am talking about the motion in the background of stars. The positions of stars are fixed, relative positions are fixed, but sun moves, okay? So, just because we are more used to now heliocentric picture. So, that is earth is moving around the sun, okay? Earlier it was geocentric only was there, you see, and so you see that sun is moving around the earth, or everything is moving around the earth, okay? So, that is the annual motion of the sun around the earth, okay? I mean apparent this thing, okay? So, that is the, and we know that sun moves 360 degrees in 365 and odd days. So, essentially one day about 1 degree. So, that is the motion with respect to background of stars, in the background of stars. So, that is the motion I am talking about, you see. And how to find those positions and all that, you see, it is not an easy thing at all, okay. Of course, moon you can see, moon position with respect to stars, you can visualize, even if you stay up, for 10 days and all that, you can see the motion of moon. But sun is difficult because when sun is up in the sky, there is no star. So, one has to deduce only. And planets and all that, you see, it is, suppose you are given all your scientific tools, except physics, laws of physics and, planetary motion and all, suppose this thing, you are equipped with all the mathematical tools. I mean, don't think it will be easy to find out how the planets move experimentally. It is, their motion is complicated, because we know now that they move around the sun, and then we have observing from the earth. So, it took thousands of years to find out how they moved and all that, and formulate laws, you see. So, then these various epicycle models, etc. were there, and laws were found, and finally, Ptolemy, of course, was there, and then Aryabhatta was there, and all these people were there, then Copernicus, and then Kepler. So, Kepler, and after Kepler can be considered as some kind of a lost great figure in kinematical astronomy. That is, you are not explaining anything using force, acceleration and all that, you are just finding out how their orbits they are considering, okay. So, that is the, but it is quite a long and very, very significant development. And see, before, let us say, Galileo and Newton, there was hardly any physics, okay. And the exact science was astronomy. Astronomy was the queen of sciences. And this non-uniform motion, you see, so that is what triggered all kinds of, developments, a non-uniform motion of the planets as viewed from the earth. So, and that is where, if everything moved around the earth and uniformly, I'm telling you, there won't be any physics and all that, This non-uniform motion, they have to account for it, they have to understand it, they have to formulate laws, So, this non-uniform motion of planets, that is what, and I'm talking about that in a simple manner, yeah.
So they calculated these movements of planets for what? Was it for astrology or was it for other purposes?
Well, that varied from this thing, from the time to time, and also from civilization to civilization. Yeah. No, in fact, astrology, there is not much evidence of astronomy in India before, let us say, 2nd century. This, it might have been, I think, came from the Greeks and others. Astrology. Okay, and surely in the beginning, the observations of planets and all that was for the sake of astrological thing, you see, but it led to huge amount of observations, you see, like Babylonians also did huge amount of observations. They might have done it for astrological predictions, but this experiment, these observations itself was extremely significant and very useful. Okay, and also in fact in many astronomy texts they will say, in India they say, oh, we have to know the exact positions of planets, you have to know this thing, because all these rituals and all that have to be conducted at the correct times. Okay, if you have to do the fasting, it has to be when the relative position of moon, sun and moon is this. Okay, so then if it is something related to the motion of this thing, so one has to know their motion. Okay, for observing the rituals and all that properly, that they say actually. Okay, but then you see, apart from that, they had some interest also. Eclipse, you see, eclipses they calculate, they have to find out when the eclipse occurs and all that, because interesting in itself. So though it started as the purpose for that, but for its own sake also they keep on doing various things. So that is what happened in other these things also, that first they might have done it for some purpose, but then in its own sake it is interesting, it is exciting, and you have to observe and you know more about nature. So perhaps that is what happened. Okay, because there are so many things, other things which is not related to rituals, but they consider in great detail, they will talk about it and all that. But the starting point, as you said, is correct, not astrology really, but correct time for religious rituals, and also astrology. Yes, astrology. Yes. Okay. So I think I should. So now, if the planet moves, planet is sun and moon also are considered as planets everywhere. Okay. They are also considered as planets. Of course, sun was considered as extremely important planets. Okay, but it was these are stated like others, but it is actually somewhat the simplest object to describe. Okay, so now their motion, even with respect to stars, is not uniform. Okay, that was observed. Okay, moon, it is very clear, it will be very noticeable even if you make observation for 1 month. So the sun also, you see, so to account for the non-uniform motion. Okay, so the non-uniform motion in the background of stars. Okay, so if this thing is going around this earth uniformly, okay, so that is called a mean planet. Okay, an average position of planet is given. You see, it's not that it is a mean thing, it is a nice thing, but the average position of the planet is called mean planet. So suppose this is there. So then they say that, I draw one more circle around that. Okay, small circle, and actually the planet is not here, but it is somewhere here in that circle, so that they specify the direction also. Okay, this one. So this is called apogee, called Mandocha in India. So it is in the direction. Now draw this. So this is the actual angle of the planet. Okay. So this is the average angle, this is the actual angle, and this is called the apogee district. Okay. So anyway, you don't have to bother too much about the detail. You can, it's very, very simple, this thing. Okay. Now the most important thing is that this actual true planet position is, you will get a formula like this. Okay. In fact, that is where the trigonometry started. Trigonometry is needed to see, sine is there, sine inverse is there, all these things come. So trigonometry is needed to explain the motion of planets. And so roughly speaking, this is this. If you take sine inverse, it's very itself, the argument itself, when that is true when it is small. So then this is the thing. So then, what is the rate of motion of this? You see, this is called the longitude or position of the planet. What is the rate of motion? You see, so then the way we do it will be modern way is just to differentiate this. You get this, right? Is easy. So this is the rate of motion. Okay. In fact, in Aryabhatta II, there is one Aryabhatta II. In 10th century, he gives this kind of a thing, So he gives essentially this formula. Basically, he doesn't explain it. He just states it. Okay. Later, Bhaskaracharya, 12th century, he discusses the instantaneous rate of motion. Okay. He says the true daily motion of a planet is the difference between true planets and successive days. Okay. So just find the position one day sunrise and next day sunrise. Then the difference is the motion in one day. So it is accurate over that period. But then he gives the Koti Phala is multiplied by the rate of motion of the Manda anomaly divided by the radius. The result added or subtracted, gives the instantaneous rate of motion. This, in fact, he gives this formula. Okay. See, they don't bother too much about added, subtracted, and all that, because cos m, you see, is either positive or negative. He says that when it is negative, you add positive, you subtract. You know that cos m is positive between 270 to 360 degrees and then 0 to 90. Between 90 and 270, it is negative, right? So it is essentially saying that. So what is very important, he says, it is the instantaneous rate of motion, tatkaliki. Okay. So he is considered as this instantaneous concept is introduced, by Bhaskara. At least in India, it is the first time. So we think that have you heard of instantaneous rate of motion, instantaneous velocity, and all that? Yeah. And who do you think is due to? The Newton. Normally, it is ascribed to Newton. Okay. So, but here they are talking about the instantaneous tatkalika gati. It's very much there. I mean, he has not explained it fully, but he gives actually one formula for this. I mean, how to get this. He never says. He says that he takes only small values delta theta. He takes that, and then he says that then the difference of the sign divided by the this thing arc is equal to cos theta. It goes as cos theta. And the geometrical argument given is this, So this is the P1 T1, that is sin theta. You just take r is equal to 1. Then P2 T2 is sin theta plus delta theta. So difference is this. Then he says this triangle and this triangle are similar, and arc is taken to be the distance itself. So then in that case you get this. No, he doesn't give any bounds and all. He said for 225 minutes also this is sufficient. This is small enough. So that's the difference is proportional to cosine. Yeah. He doesn't say go to infinitesimal. But he does later he will say, say like sin theta plus 1 degree. See, that is 1 degree is even smaller. This is 3 degree 45 minutes. He gives the correct thing. See, is r sin theta plus r cos 1 degree into this thing. He gives that. So, so everything is not fully, defined precisely, and it is not that, but they are there in a way. Yeah. Okay. So this is he gives the geometrical reasoning. Later, one Nilakanta Somyaji will come to him in a Kerala school. Yeah. Yeah. No. There is, because they talk about it. Like Bhaskara, he keeps on talking about his predecessors. He talks about Brahmagupta's. Oh, the great Brahmagupta. And then Manjulacharya. There was a peer group, I think, because these are the main important. There is one Lalla. Okay. Then there is one the Sripati. So they refer to those people, you see, and they are considered the important people. And then later Kerala people, they talk about Bhaskara and many others also. They refer to those people, you see. Well, that also one of those historians, K.V. Sharma, you see, in whose name the foundation is there and I am there. So he says, of course he takes, I don't know whether he proves it, that there are some kind of a meeting in a place in Kerala where they defined, the this thing, done the calculations so that epoch, etc. was changed. They seem to have, but it got transmitted. That is very clear. You see, for instance, Aryabhatta, the one number one, he was in Pataliputra, so that is Patna, modern Patna. Whereas Bhaskara one was in western part of India. So he is commenting upon it. So naturally there is a flow. And this one, Varahamihira. Varahamihira is supposed to be from Ujjain, you know. Ujjain. So that Varahamihira, just after 40 years of Aryabhatiya, he is already quoting Aryabhatiya, you know. Yeah. So there was communication was there, you know. So that is not surprising because, you know, even religious texts and all that, they, why within India? They went to China and all that. No, they took manuscripts and all that. So a lot of transmission was there, you know. Yeah. Not only within India, but from outside also. Things like that. Yeah. And maybe this epicycle idea might have come from outside, you know. I don't deny it, you know. This epicycle, afterward they developed it according to their this thing. But the idea might have come from Greeks. And there's a lot of Greek kingdoms and all that in the, you know, in the earlier beginnings of the first century. So maybe, yeah. So there was transmission, yeah. This Nilakanta takes this itself, he is more accurate, and he gives this formula for this, you know, the rate of motion. Of course, he didn't say this. He will not say it like this, but he will give the rate of motion. And he gives this is the thing. See, which is equivalent to taking the derivative of sine inverse. See, it is not an easy thing, you know. Even now, I think people slightly difficult to find sine inverse d by dt. But he has given these in 1500. Okay. So what he says is Chandra Bahuphala, you see. So that is R sin m. Varga is square of that. Varga Shodhita Trijya-kruti. Okay. Trijya-kruti is R square. Okay. So this is subtracted from that. Pada is square root. So is something is divided by the samhare. Tatra koti phala liptika nam, you see. So this is that. Kendra bhukti, that is this. Yacha labhyate tad vishodyato tat samayaja. That is the instantaneous velocity, you see. You also do. That's how it is expressed. There is what can be considered as a Kerala school of mathematics. So people think why only Kerala it developed. Maybe because it was relatively peaceful. That is what they say. You know, in the 15th, 16th century and all that. There are too many invasions and political turmoil in other parts of the country. Kerala was slightly free of that. But of course, there also it came after Portuguese came and this, that and all that. So probably it was more related to the fact that it is this, you know, this is more peaceful. And also the social structure was such that some people could devote a lot of time for this, you know, kind of a thing. So that's what they say. We will not go into that. So that the Madhava of Sangamagrama. So I am talking about this Madhava series, you know. And then his student is called Parameshwara. His son is Damodara. Damodara is the student. And Damodara's son and disciple is Nilakanta Somayaji, who wrote this one Tantra Sangraha, which we have worked on, and a big commentary in Aryabhatiya. And then Yukti Bhasha, which gives a, interestingly, it is in Malayalam. Okay, well, I don't know Malayalam, but one scholar was there who was from Kerala, so he translated and we explained what is there in that. Okay, but it's also the Sanskrit version also is there. Okay, so up to 19th century beginning, there was a lot of development in that. So Yukti Bhasha has mathematics and astronomy, two sections. And in the mathematics section, much of mathematics known to Indians at that time is explained. It is really a textbook for students and systematically developed the subject and is self-contained. Okay, so it starts from numbers and all that, you know, how to multiply, how to divide, starting from that, square root, cube root and all that, and then quadrilaterals and cyclic quadrilaterals and all that. And finally, he comes to circle and relation between diameter and circumference. See, because they knew that that is little hard. So its proofs are rationales. Yukti is called, you know, this thing. Proofs are rationales for all the results. It is there. So So we'll concentrate on calculus concept in Yukti Bhasha, basically infinite series for pi, and if time permits, some integration methods. So first they start with Yukti Bhasha, 15, you can say around 1530. Okay, so it's supposed to be commentary on Tantra Sangraha, that is 1500 exactly. So finding circumference of a circle by circumscribing polygons on a circle, circumscribing or inscribing. Okay, so that is Archimedes also did that. Okay, a long back. So then many people have done, Bhaskara 1 have done it, and many commentators have done it. Bhaskara 2 also has done it and all that, you see. But you have to, for accurate things, you do have to do large number of sites, you see. So that is very difficult. It's absolutely impossible to handle. Square root of all kinds of things come. So is it possible to do it without this kind of this approach, a new approach? So that is what they are saying, you know. So they say that, and then what they do is, so this is a square, so this is the quarter of a circle. So now this side is divided into n equal portions, okay, equal, and then join it to the origin. So then these are the arcs. So these are equal, the arc bits are not equal, obviously. Initially, of course, the arc bits will be essentially equal to that thing, but afterwards they diverge this thing, okay. So these are there is a geometry he takes. So now he takes this triangle, see this triangle and this other triangle are similar, so you get this. So I don't have time. So basically, when n is large, this, you know, this side of the triangle is the perpendicular side of the right angle triangle, and this is essentially arc bit, you know, when n is large, they are very small. So this r by n, sorry, this radius you can take it to be small r, okay. So this is a mistake, it's a smaller radius of the circle. So r by n is the number of divisions here, so it is this, okay. So arc bit is this. See, this is the 1/8 of a circumference, right? This is 1/4, so half of that 1/8. So that is this. It is the sum of all the arc bits, and arc bits are taken to be bi only, so you get this. So now in summing it, the I is equal to 1 to n. So it is not easy because in the denominator this I is there, you know, I squared is there in the denominator. So how do you handle that? So they have a very nice strategy. What they say is, you know, he says is the Yukti Bhasha, see, take c by b, okay. So now you can written as, suppose, you know, you make it as, suppose you have to bring c to the denominator. So what you do is, c is b minus of b minus c. So 1 minus b minus c by c into c by b. Now again use this c by b into this thing. So like this. So c by b is this infinite series. Okay, simple. They just you are just using this and keep on doing that. Okay. So c by 8 is this infinite series. I is equal to 1 to n. Okay. So you got summation of I squared, summation of I to the power of 4 and all that. And we have to find this I to the power of k, 1 to the power of k up to n to the power of k. So then they use a trick. See, you know that 1 plus etc. up to first power, in the 1 plus etc. up to n is n into n plus 1 by 2. All of you know. Okay. And for very large n, if you can ignore n, so it is approximately equal to n squared by 2. So next is actually they will show that organizing these terms properly, you see. In fact, for this, they write it like this. Now, this what they do is n, okay. So then reverse it, you know, n minus 1 plus n minus 2, etc. So now everywhere n is there. So n into n, then minus 1, minus 2, etc. So finally they get this. Similar strategy they use for this. Okay. So I will not go into that, it's little. So finally they get, so essentially what I am saying is 1 squared plus 2 squared plus etc. up to n squared is close to n cubed by 3. And similarly for the higher powers, I to the up to kth power, there is n to the power of k by k. See, this also you know in a way, right? Do you remember the formula for sigma 1 cube plus up to n cube. No, yes, sorry, 1 squared plus etc. up to n squared. Yes, n into n plus 1 into 2n plus 1 by 6. So, for very large n, it is n cubed by 3. 2 is there, so 2, 6. So, n cubed by 3. Now, denominator n cubed is there. So, you can ignore the other things for large n. So, that is the strategy. So, you get this. And they give clever argument they will show to this, show that this. So, C by 8 is this. So, this sigma I squared we know, sigma I to the power of 4 is known. So, this is geometrical. And tan inverse you get is quite a simple this thing, What is happening is, yesterday you were asking, see you had done this arc, C by 8. So, instead of that, suppose you stop here, do up to this. Okay. So, suppose this is theta. You take it as 1, yeah. Okay. So, now this is very clearly tan theta. You call it as x kind of a thing, So, instead of this, what you get is, C by 8r, instead of that, what you get is, theta, because you are finding the arc in terms of this thing, So, instead of this powers of r here, you get powers of x. Okay. So, what you get is theta is equal to 1 minus etc. So, now you put tan theta is equal to x. Okay. So, this is, you get the tan inverse x series. So, they mentioned that also, they mentioned this. Yeah. So, tan inverse x series is this. Okay, yeah. Tan inverse is x, yeah. X minus x to be etc. Yes, yes. Yeah. No, sorry. Yeah, right. So, this is theta actually. This must be theta. Yes. Yes, you are right. Yeah. The Gregory's. Yes, so called. So it is given. It is certainly, and this is proved in Yukti Bhasha, but they always ascribed the result to Madhava. So at least 14th century, nearly 3-4 centuries separation is there. Yeah, 300 years easily. Yeah. R is 1. I have taken it to be 1. Okay, so yes, it is the r theta is equal to r theta. R factors will come. R factors will come, that's true. So, when R is put equal to 1, you get this, tan inverse x. Yeah, you are right, sorry, of course. Yes, thank you. Yeah, that's what you said, right? Yeah, correct. So, this is what it is happening. So, essentially here R, R is coming. See, R minus all these things will come. Okay. So, whereas here, so it is, yes, exactly, I will coming to that. So, now this is a very called a slow convergent series, 1 minus 1 by 3 etc. It slowly converges. I mean, even to get to about 2-3 decimal places, you have to take about hundreds of terms. Okay. So, you have to have some fast convergent methods, series were there, and they have done that. So, what they do is this, by some manipulations, they say that you truncate the series here. Truncate the series here 1 over 2n minus 1. It comes here better, yeah. And then the rest of the terms are summarized in this. So, this is called a correction term. So, with this correction term, and they prove it also, there is a method of proving. Yukti Bhasha, there is a method, how do you get this correction term? So, this error correction analysis is, is very much there in Yukti Bhasha. In fact, we went through it in detail. There is a lot of confusion for decades, a lot of people said, how exactly is the correction term was known. But we saw that it is there in the text itself. One has to go through carefully. So, correction term, how to get it? So, that they have done. And if using this, if you instead of this, if you take this and n is equal to 50, then pi is correct to 11 decimal places. And for better things are available for this, and then pi was calculated corrected to 17 decimal places by Raja Shankara Varma, 19th century beginning, Cochin, associated with the Cochin kingdom, And similarly, you have got infinite series for sine and cosine functions. That there some strategy is somewhat different, some iterative method is used for finding this series. We have worked on that. So now this integration also is there, using this delta sine theta or delta cos theta is minus sine theta, delta theta and all that. You can find the area of the sphere, 4 pi r squared, and volume of the thing. All these things are also written in Yukti Bhasha. So I think I will stop here. I think if there more any discussion can be. I think probably they might have written somewhere. I don't remember exactly. Possibly, yeah. That's 4 pi r squared. Yeah. So that yeah, maybe. I'm not sure about that, but yeah, probably yes. I think they did write it in terms of this thing. I think by using some various inequalities and all that. Archimedes might have. I'll check it. Yeah. But Bhaskara, what he does is interesting. Bhaskara himself, he doesn't do our usual integration. What he does is it's going. The slices, the signs, you have to sum the signs. He will actually sum the signs. Bhaskara. He knows the sign table, and then he gets a value close to pi, okay, his value of pi, and say, no, it must be that. So, but he actually sums it, but integration concept is there. Whereas in Yukti Bhasha, it is, this is used. There is a cos theta, etc. will, yeah, cos theta, intermediate terms will cancel, you will get exactly this, It made use of the fact that delta cos theta is minus sin theta delta theta. Just one this thing, Mr. Subramaniam yesterday was asking, when made some remark. He was saying, okay, I mean, you are getting all these results and all that. So how did they develop it? You see, like somebody has come to some this thing, he has developed some results up to some level and all that. Then afterwards, was there a mechanism where people will take it forward and get some new results or generalization and all that? Yeah, I can use straight away one example. Okay, so you can write it as sigma r is equal to 1 to n, right? So this is n into n plus 1 by 2. So this is called the first sum. So then Aryabhatta also considers the next this thing, sum of sums. Okay, sigma r into r plus 1 by 2 in fact that can be shown to be, this is there in Aryabhatta. See, up to this they knew. So, but further, it is not that easy, okay. Some of these things and all that, Then there is one Narayana Pandita in 14th century. He used the kth sum. See, you call it as first sum, you see. Then you call it as second sum. Sum of sums. Then, so this can also be written as, you see, sigma r, I can, symbolically, you can get second sum, okay. So what is the kth sum? So he gives the result as he generalizes this. Yeah, he gives this. He gives result. And this is crucially needed for the infinite series for sine and cosine. This. So this also this thing, how did this transmission and all that, you see. So probably these people know this Narayana Panditas were Kerala people, you see. It got transmitted in some way, okay. So then this result is very much needed for finding the infinite series for sine and cosine. Yeah. Yeah, you see, trigonometry, in fact, that's what I said that Bhargava also was telling, that sine function, you see, using it as a function and doing various things, you see. See, that is characteristic of India, you see. Whereas and you give algebraic formula for that and manipulations with that. Whereas in the Greeks, they had only geometrical things, see. So they wouldn't move forward, you see. Yeah, so the function is very much there, sine and cosine function it is very much there, okay. So later, of course, now you say that it is a map, you see, function is a map and other. So that is later development. Yeah. We close to function, yeah. So up to 15th, 16th century, let us say 16th century, they are, somewhat more advanced, I will say, in general, yeah.